Thanks for having me here. As I hope that was said in German, the presentation will concentrate first on autonomous driving technology. That's going to be the longest introduction to the topic itself, which is how, from a deep understanding of autonomy and technology for autonomy, how does connectivity fit in, what kind of roles is it going to take, and what kind of discussions does it bring forth. Mobileye has identified three areas where there are very challenging problems, or three pillars of realizing autonomous driving. The three of them would be perception of the environment in full, understanding where you're driving, what's around you. Mapping the environment, we will link the two in a second. We'll talk about what's the purpose of mapping, what does it serve, why is it critical, why is it just beneficial. And driving policy, which is the ability of the critical ability of the vehicle to negotiate its way after it perceived the environment. So just for a very easy mental image, these are the three technological pillars. Technologically speaking, they also have a very interesting three types of intelligence or artificial intelligence. First one would be considered what's called supervised learning. The last one is unsupervised or reinforcement learning. We'll understand it as we go on. Mapping is, of course, the wisdom of the crowd, and we'll talk a lot about that. So, first of all, Mobileye was established as a computer vision company. We've been working on harnessing the visual space, which is perceptually complete. Any one of you drives the car based on your eyes alone. All of the information is there. All you need to have is the brain that translates this raw data into meaningful perception. Meaningful perception is what is the environment model around us. And for the rest of the discussion, it's also important to touch upon what would be such a description of environment model. It should consist of the boundaries of your drivable area. You need to understand where these boundaries are. The geometry of driving paths within that area. How are other vehicles and yourself about to conduct yourself within that environment. Movable obstacles, anything that is not part of the static environment. That could be these vehicles or a pedestrian crossing or a pedestrian just walking along the sidewalk and needs to be taken into account. And last one, very important, semantics. It's a very broad family of perceptual information. Could be the color of the traffic light, something very explicit, but it could be something more implicit as the way that the pedestrian is currently looking at his phone, which is a very important semantics to how you should be driving. So all of this information is contained in a visual space. And furthermore, I'll offer you another point of reflection about your eyes and what they do. Computer vision has internal redundancies. What do I mean by redundancies? You have a sense of something in front of you from many different perspectives. Let's look at it more technically for a second. Here it is. So we have a 2x2 matrix, just really to encapsulate how computer vision approaches perception problem. You can analyze the foreground, the object of interest. Let's see if I can run it again. Probably not. Let's go back and run it again. So here it is. So you can either analyze the foreground of the object by means of appearance analysis or by means of optical flow analysis. Then you have a sense of that object. Alternatively, you can analyze the background in terms of appearance or optical flow. These are the two things that you, as humans, these are basically the bucket of four things that you guys are doing as part of your perception, and it gives you a very important sense of redundancy and robustness. Even if there's an object that you never seen before and are not able to classify what it is, the sense of optical flow will tell you that you're about to hit that object, and it's very important. So that's as far as perception. We'll get back to it when we tailor all together with other sensors. let's talk about mapping for a second. We mentioned that as part of the environment model, there are 4 elements, one of which was the geometry of your driving paths. Now, in terms of redundancies, all of your environment models should be sensed robustly, should be sensed with more than one source of information. As for other elements, you can use LiDARs or radars, for example, for vehicles or pedestrians detection, or the boundaries of your drivable area. But when it comes to geometry of driving lane, the only source for that is a camera. A failure in the camera has to be backed up by something, and that something is a map. That's the role, the critical, safety critical role of a map in autonomous driving. It has, of course, an additional role, which is the same as you drivers reach a road that you're familiar with, you can drive more fluently and efficiently. So that's a sense of foresight. So to complete it, the map serves robustness for lanes sensing and foresight for the road geometry that you can conduct more comfortably as you move around. Now, Mobileye's approach to the safety critical role of the map suggests that it has to reflect reality very, very faithfully. The map cannot be disconnected to the actual reality. If there's a change in the road, if there's a new construction area set up outside of your house, your autonomous vehicle should be aware of it. And Mobileye's approach for that is to harness our important asset of single camera equipped vehicles, lower end non-autonomous vehicles, to help us map the environment continuously. We currently have 15 million vehicles installed with cameras, and the next generations of these vehicles will include a software that helps us map the environment. So let's look at how it happens very quickly. And this, of course, suggests a discussion about connectivity. This is harvesting. This is what the vehicle is collecting as it drives through the environment in real time, only using a single camera and a GPS. We construct these small map snippets that you can see downstairs. Okay? These map snippets are sent up to the cloud and are aggregated dynamically and continuously. Okay? We will discuss also, as part of the summary slide in this area, data sharing models. How do we incentivize sharing of data? How do we make benefit? How do we serve the mutual benefit of car companies that have very effective fleets to do so? The third element is you have an autonomous vehicle that needs to use that map. So it needs to be able to localize itself within that map to gain the redundancy that we talk about. What you see on the left here, before we play the video, this is not perception in real time. This is the map projected to the image. So after we know where we are in the map, after we localize ourselves in the map, we can gain that redundancy that we were looking for. We project the map to the image, and if for some reason our perception doesn't work, we have a backup for lanes perception. So let's look at the actual results. And again, recall that what you see on the left side is a result of map that was constructed in the cloud, downloaded to the vehicle, and the vehicle is executing this localization using all of these landmarks. Play it back again. Okay, all of the points that you see here are landmarks that help us localize all of these points. Landmarks that help us localize within the environment. We talked about the concept. As for how do we merge map and image, I'll just go down to the bottom line of it. The most important thing that we preserve in our approach is semantics. Okay, a camera can tell you in which lane each vehicle is, and this is very critical information. Camera won't be able to tell you naturally, at least, at very high accuracy, what's the distance of the vehicle or what's the distance of the lane, but it can tell you very, very clearly what's the relative distance between them. And that's, again, what you as humans are doing. You have no perception, no sense of the distance to the vehicle in front of you, but you have clear semantic perception of in which lane it is, what it's probably going to do given that lane geometry. And this is what our approach is preserving. I won't go into the details of what it means, but it just says we use the map as a source of road elevation information as well, to be able to translate from image coordinates to world coordinates, to 3D coordinates, in a way that helps us preserve that semantic accuracy. Let's look at it in a video. Would be much easier than me mumbling. Let's play it. So what do you see here? This is a three-dimensional perception of what goes on around us. Okay? It's only based on a camera. So the three-dimensional information comes from understanding that understanding of the three-dimensional structure of the road from the map. What we do then, we get the three-dimensional understanding of the road from the map, take it to the image, and now we know how to map back to 3 dimensions all of the objects that we have. So you can see that the lane assignment of the object is accurate to very, very far ranges. Alternative approaches would try to build everything in 3 dimensions from separate sources, which could jeopardize that important semantic accuracy. So again, we're trying to be, along the time of Mobileye's history, we've been faithful to the philosophy that a human drives based on its eyes. All of the information is there. What do we do in order to make it work as humans, as drivers, is what Mobileye is working to instill into the chip. Let's talk about that. That was then perception and mapping and the interplay between them. To summarize very quickly, we have an environment model, understanding of the 4 elements of the environment model, and how mapping serves one of these elements, which is the road geometry. We also discussed the way to integrate these two, perception in the camera and a map. What's the right model for integrating these sources of information? Now the last one would be the third pillar, which is driving policy, decision making. So the common approach to functions that are of lower level of autonomy is a rules-based system. If you take adaptive cruise control systems or lane-centering systems, they have a very simple task: keep within the lane, avoid other targets. You can really code that set of rules. When we're moving to a higher level of autonomy, the challenge of covering the entire spectrum of possible scenarios by a set of rules is intractable. That's not the way to approach it. And Mobileye has been working on a machine learning-based approach to study the strategy and the negotiation skills of a human driver. How do you, by your action, the complexity, of course, is that your action affects the environment. That's a closed-loop thing. So the machine learning framework for that is slightly different than a perception machine learning framework, as I mentioned. It's called reinforcement learning, but the outcome of it is learn a strategy. Not unlike the AlphaGo that you've heard about, the strategy in a game, the Chinese game. Not unlike this kind of set of tools. You want to, the tree of possible options is infinite in that game, so it is on the road. You need to be able to use machine learning to scale it up. Otherwise, you reach a very common situation with autonomous driving where there is some exceptional situation where they just stop, fall back. There's a truck in the middle of the road and I have a dashed lane, done. And humans have a sense of the rules of breaking the rules, I think. Also when interacting with one another. It's very important to make the traffic flow. So this is here's a nice example, by the way. We treat the double lane merge as a very interesting, important example of negotiation skills. All of the agents that you see here are carrying the negotiation skills that we trained them to have. What they need to do in this particular case is that their blue cars need to go to the right, red cars need to go to the left, and if there are conflicts, they need to resolve them between them, slowing down, speeding up, decide when to change the lane. They even make decisions of stay to the left of the lane to signal that you want to move. That's another thing that you guys are doing as humans. So a very powerful tool. We don't rely on rules for conquering this problem. And we have a very clear safety model that we discussed. It's not just a black box that makes decision. We have very clear ways, as we do with other elements of perception, of guaranteeing safety, given machine learning core. Just to hint, the discussion about data here, or connectivity, is mainly about being able to train these agents through that very effective million-hour driving class. And to make that million-hour driving class effective, it should be very good representation of the real world. In order for it to be a very good representation of the real world, we need to capture scenarios from the real world from a very broad base of harvesting vehicles. We should record situations and make sure that the agents undergo a driving class that represents these situations. Okay, we'll touch upon, we'll close that on the last slide, but just to have that in mind. The video doesn't work, but it makes the point here. The roundabouts are a very, very great invention, one of the biggest inventions, I think, in transportation in a few years. But they avoid these very dangerous situations of head-on or side crashes, but they really drain it down to the problem of double lane merge. That's exactly what happens here. You enter the sorry. Yes, I have that. You enter the roundabout and you want to exit somewhere, and the other person enters here and wants to exit another place. And that's a classic case where the negotiation is becoming very, very critical. There was a nice video here that trashes the driving culture in Israel, but take my word for it. Just an interesting set of statistics, and that's also to capture the fact that we have a very formal safety model. Over 100,000 runs, again, in the simulator, 100,000 runs of this experiment after we trained the drivers, the agents, 0 accidents, and 99.8% success of negotiation. So in 0.2% of the cases, vehicles just went to the wrong way. They didn't accomplish what they wanted. Not unlikely also for humans. As I mentioned earlier, very similarly to HD maps, there is a very interesting ground here for information sharing, collaborative information sharing. The sharing of scenarios is what's going to drive the development of negotiation skills. That's a bit technical. Let's try to let's skip this one and explain the model here just to conclude for the last discussion slide. Our methodology, I'll say what I was reading in the previous slide a bit too technically, is the following fact. When you're fusing several sources of information to make a decision, you can either fuse them in a way that serves safety, a very paranoid manner, that's very careful that any evidence from any source of information triggers you, or you can do it with something that demands robustness and demands cross-validation. And sometimes the structure of these things come as a trade-off. You either create a system which is overly defensive, overly triggered, or a system that's requiring too much evidence and may run into accidents as a result. The way that we try to decouple the problem to avoid this trade-off is that we build the first part that I mentioned, requiring redundancies and etc., is what you would think of as intersection of sources and synergy between sources. That's the first element. If you deploy this intersection of evidence, demanding intersection of evidence only for planning your trajectories on the long term, okay, you're creating a risk of misdetections. You're not very paranoid in that case. But you still just plan your path ahead, and then you have safety checks for the trajectories that are more paranoid, that are more careful. And this helps materializing this kind of, 1 second. Can I ask you to play that one? I'm not sure I can. Thank you. So this is, you can see synergy between LiDAR, for example, that's the red and orange dots, and a camera. Sorry. And here you can see examples where we are provoking our reinforcement learning core with short ghost detections or short miss detections, just to make it robust to these artifacts of sensor fusion. So we are separating comfort from safety at the decision-making level and simplify the work in the sensor fusion level. As I mentioned earlier, there's a lot of room for synergies between the different sensors. Several nice examples that I thought would be good to share with you guys here is, of course, map and camera, which we already discussed. LiDAR and camera for robustifying the distance estimation as another way, redundantly to this approach, you can also use depth sensors to get that sense of scale that we're missing. This is a very nice example. We have very elaborated technology for road surface analysis using optical flow, and we're combining it with LiDAR evidence to get this perception of the geometry ahead of us. Some more nice examples. For free space detection, boundaries of where you can drive. The camera, in this case, was going all the way green, but it's hard to see, but there is a bar here in the entrance. And the LiDAR sensor captured it. So if you can see, there's a white line here that captures the synergy between them. On the other hand, a camera is very good in perceiving this textural boundary that's not part of your drivable area, but no depth sensor can tell you that. There's nothing there. It doesn't mean you can drive there. So this is a kind of a effective handshake for free space detection. That said, again, these are the synergies that we're extracting for planning the path ahead for comfortably, and then we have very strict and very paranoid sensor by sensor tests of these planned trajectories. Okay, let's move to the last slide discussion about the connectivity. That's another just nice example of the vehicles making by themselves they prefer the trajectories that either go very slowly next to the vehicles or faster but going away from the vehicles because of the risk of being surprised by a cyclist. And again, you guys do the same. It's just nice to see that we don't need to program it. We can just train the computer to do it. So connectivity in the service of AV, and I know it's a bit one-sided. Let's start with what's not mentioned here. Autonomous driving makes the vehicle a huge sensor. Okay? A huge sensor is a driver for data market. A huge sensor, data market will drive connectivity. So there is an interplay on the other way. I'm centering on the AV using connectivity in this slide, and let's look at it. How do autonomous driving will use connectivity? As I mentioned, in all of the three cases, data access to data is critical for all three pillars of autonomous driving, both for perception, mapping, and policy. That's not a surprise, but it's important to touch upon it. Technology and data access are becoming the same because technology today is data-based training, data-based learning. It's very, very important. As for data handling, a nice analogy I'd like to make in this forum is that there is critical value in sharing data in autonomous driving, and the analogy would be to nuclear energy. If it's contained, it's socially beneficial. If we can guarantee that the information is not used to harm anyone, that social benefit will be harvested. We have to make sure that we have the tools in place, at least for the pieces that are critical for developing the technology, not for the pieces that are going to serve the service providers or the marketers. Talking about the sharing of what's going on our roads so that we can build technology to improve that. So we need to be able to assure anonymization and containment standards that unleash this potential social benefit. Important question. Communication systems, when we talk about hard, real-time, or safety-critical elements in autonomous driving, there are very, very strict models. I'm not sure if the forum is familiar with formal integrity models of sensors and systems to assure autonomous driving. The way for communication systems to reach these high integrity levels, that's how it's called, AC levels, is still long. It usually involves a lot of duplication, and it's not very economical. Not at all, actually. So building a vehicle with the redundancies that are needed to secure these redundancies, also at the sensor level, the compute level, are very expensive endeavor. The communication market is not built for that safety critical role, not yet. I know, for example, in the US, the mere fixed costs of the infrastructure without aiming for this kind of redundancies and integrities are pulling the market, are a very hard cost burden on the market. So I would want to suggest that communication more immediate role is in near real-time values. For example, mapping, as we discussed, let vehicles communicate changes in the map and other vehicles enjoy from that map. It doesn't have to be hard real-time. There's a lot of processing in the middle, but it's still very important information to communicate. Traffic optimization, that's not safety critical, but it's another social benefit. We can use connectivity to manage fleets to optimize the use of traffic, use of roads, use of gasoline, use of electricity, everything. Offline data communication goes without saying. We need a way to offload information from the vehicles in a way that serves these machine learning cores. And safety assistance, and I insisted on writing assistance because we cannot build the technical safety concept of a vehicle on fully available hard real-time communication system. It cannot be done. It's not where the technology is. We can definitely benefit from a great example. Car-to-car communication is one example. It would be great if all vehicles had car-to-car communication, any old vehicle traveling on the road, any pedestrian traveling on the road. But since we cannot assume that, it can only assist in safety. Okay, that's very, very important point to make about the role of connectivity. And last, of course, is the economy of data sharing. Perfect. In the REM, the mapping, REM is road experience management. That's the crowdsourced mapping that I shared with you guys. We've been able to establish a model, an economical model that incentivizes the market player. We created a marketplace for them to upload data from their vehicles and to take in on the revenues coming from that asset. It works in some cases. In this particular case, REM, it works. Could very well be that for driving situation sharing and other less immediate things, less immediate values, there needs to be some regulatory or centralized, at least, data sharing model put in place. These are my thoughts for today.